Good afternoon, everyone. You are looking live at us. Welcome to GeoStrata Extra. I'm Brad Keeler, the director of the Geo-Institute. If you don't know much about the Geo-Institute, we are a technical society that's part of the American Society of Civil Engineers. We have about 12,000 members, most of whom are geotechnical engineers and or geologists. Welcome to our first live stream of 2021 and our first GeoStrata Extra of the year. Hopefully you're familiar with GeoStrata. It's our magazine that's published 6 times a year. Last summer, we launched this show to give our members a little bit more virtual content while they were sequestered in their homes. We choose an article from every issue and go beyond the text with the author. You can go back and watch last year's episodes on this very YouTube channel, which brings me to this. If you like what you see today, and I think you will, click the little subscribe button you see below this window, then click Get Notifications, and you will be notified every time we post a new video, which is frequently. We are thrilled to, for the first time, have a sponsor for this episode of GeoStrata Extra. Our sponsor this time is Aero Aggregates. Aero Aggregates of North America produces ultra lightweight foamed glass aggregate from 100% recycled glass. The aggregate has a dry bulk density of 15 pounds per cubic foot, high friction angle, and is DOT approved. The glass aggregate has a closed cell structure which will not absorb moisture and provides long-term durability. And you can learn more about it at aeroaggregates.com. Today's episode is a conversation with Scott Anderson and Michael Beatty about their article on numerical modeling for site investigations. It is from the January-February issue of GeoStrata. Here to interview them today is GeoStrata Editor Jeff Dunn. We have one reminder before I kick it over to Jeff. If you have a question, or should I say when you have a question for Scott and Michael, put it in the chat box to the right of the viewing window. Please keep your questions topical, and we will try to get to everyone's questions. Now, gentlemen, welcome. Thanks for doing this today. And Jeff, over to you.
Thank you, Brad. And to echo what Brad just said, welcome to the first edition of GeoStrata Extra in the new year. We've gotten past a peaceful transition of power and now back to some important geotechnical engineering issues. As mentioned, my name's Jeff Dunn, and I'll be the host and inquisitor or questioner today. And give you a little background, I'm a senior principal and single practitioner consultant with R.J. Dunn, Geotechnical Consulting in Walnut Creek, California, near San Francisco. I've been an editor of GeoStrata since 2004, which is, I'm surprised how fast the time's gone. But this is my first time doing an interview on the internet. I've taught college courses on TV, but now I'm hoping for a little bit of internet fame and maybe become a geotechnical influencer in a second career. Now our speakers and authors, Scott Anderson and Michael Beatty, give you a little introduction to them. Mr. Anderson is a senior geotechnical engineer with HDR, and he has over 26 years experience in preparation of geotechnical engineering analysis and reports, addressing design and other geotechnical tasks for a wide variety of projects. His work has primarily concerned dams, levees, earth retaining structures, bridges, towers, slopes, and nuclear facilities. His specialty, and where he's quite an authority, is numerical analysis of earth structures with finite element, or FEM methods, and finite difference methods, or FDM software. And the software he uses fairly routinely and knows the best, I guess, these days includes Soil Vision, Plaxis, and FLAC. Of course, some of the widely used software that's available. Michael Beatty, Dr. Beatty is an independent engineering consultant with 35 years of experience in geotechnical and earthquake engineering, numerical analysis, and soil structure interaction. His work projects typically involve embankment dams, foundations, ground remediation, transportation, buried pipelines, and slopes. And many of these projects include estimating the occurrence and effects of liquefaction in sands, gravels, and low plasticity silts. Dr. Beatty has performed both static and seismic nonlinear deformation analyses of geotechnical systems for over 20 years using the computer program FLAC. And his use of finite difference techniques to analyze liquefaction and resulting deformations includes co-authoring the UBC sand constitutive model for the analysis program FLAC to fit in with that. Michael is currently an independent consultant providing geotechnical and seismic analyses, peer reviews, site characterization, and technical oversight for public, commercial, and international clients. He's a principal engineer at his firm, Beatty Engineering, located in Beaverton, Oregon. So that's an introduction to our speaker, or speakers, I should say, and authors. Just to let you know, while I'll be questioning our authors about their paper and article related to numerical modeling, I'm not a hands-on modeler myself, but I learned about numerical modeling back in grad school, and I ran some programs and wrote some programs back in the day when you had to key punch cards and you ran with Fortran 4, so it wasn't the most user-friendly. I referred to it as user-hostile. I don't do numerical modeling these days, and I haven't for a number of years, but I've worked on a number of projects where numerical modeling was done in some incredible numerical modeling efforts that have included dynamic models and robust models that were structured, the interaction of soils and rocks and structures in the subsurface, and modeled large earthquakes over large areas of downtown city areas, or worked with models that looked at existing deformations in deep excavation shoring systems and predicted potential movements in the surrounding area and the potential to impact existing structures. So I know that they have a great deal of potential to be used and provide a great deal of information, provided they're used properly. And that's what we want to get into today. And what is one of the main facets of this article is a succinct overview, and we're going to elaborate on what's published in the article, but how numerical models can be used and what's important to put into those numerical models. Not just running the model, but the old adage of if you put garbage in, you get garbage out, or is used, I know it as GEGO, to use that acronym. So with that, and to remind you, like Brad said, if you have any questions, feel free to type them into the comments for this video feed, and we'll do our best to address them as time allows. So with that introduction, welcome Scott and Mike to GeoStrata Extra, and I'll ask you first off, some of our viewers might not have had the chance to read the article yet. It is posted online, and I know the issues are, if you haven't received your hard copy issue, they're in transit. But Scott, can you give us a short summary of what the article is about and covers?
Yeah, I can do that. Essentially, it goes over what site characterization means to numerical modeling, and what you should be looking for in terms of the different types of soils, geomorphology, geology, and gives a brief overview of those type of things to look for while having your mind on a numerical model. And then it goes over a little bit about the different types of constitutive models that are available. Of course, there are a myriad of models that are available. So space constrained, we went over approximately 5 of them that are available out there, and mentioned quite a few more. And then we went through the calibration of numerical models to site characterization and laboratory testing. And then we give you a little bit of why it all matters at the end.
Okay, great. Thanks for that summary. I guess, Scott, starting with you, and then Mike, we can have you present your answer as well. Question for both of you. How did you happen to get into numerical modeling and become known as a modeler, which I hope you're okay with wearing that kind of moniker? Scott?
Well, I happened to get into it working on my master's and working at Sandia National Labs, where I worked on a lot of different finite element programs, modeling municipal solid waste landfills back when interface elements were new, and we were trying to model geomembranes in solid waste landfills. And so I just happened to fall into it as part of my studies, and grew to enjoy the challenge of developing numerical models and finding out all of the little gotchas that the programs have. And it's just been an enjoyable experience over the years, learning more and more.
Okay, great. How about you, Mike?
I was fortunate in my early career. I had a job that really touched on a lot of aspects of engineering. And one of those aspects that I was assigned and I really enjoyed was doing seismic structural analyses. And I used, very outdated programs now, SAP4, Strudel, programs like that. And I liked your term user hostile because we didn't have to punch cards, but it wasn't much beyond that. As my career developed beyond those first years, I started doing geotechnical engineering and found that I really liked that as well. That soils were just a very fascinating material. Kind of started off being interested in concrete and steel, which is pretty relatively well understood compared to soils. And after 10 years of working and getting my master's, I had the opportunity to do my doctoral studies at University of British Columbia. And I was able at that time to combine those two interests, the geotechnical and the numerical modeling, particularly seismic response, and have been not 100% of the time, but most of my career since then is focused in that area.
Oh, great. That's interesting to hear, Mike, because I remember back in my college days, I felt kind of the same way. Concrete, steel, and timber seemed like well-behaved materials, whereas soil, you couldn't dictate that much to. You got what you got within reason. Right. That was an attraction to me to the field as well. Well, moving on to the meat of the article, one of the key things, Scott, you touched on it in your summary, was the evaluation of site geology and depositional environment, which, we look at it in geotechnical engineering, it seems fundamental, but you really emphasize in your article, and I think it's very important, that those have to be evaluated. They need to be considered in any kind of numerical modeling effort or scheme. But I wonder, what in your experience, and Mike, I'll point this one to you first, do you see that that's done routinely in sufficient detail to support your modeling work, or kind of what's the standard of practice that you see?
I'd have to say it's sometimes done at a good level. You definitely see that. One of my work tasks that I'm fortunate to have is to be able to do peer review or be involved with what a lot of different companies are doing, which has given me the opportunity to see that in practice, there's really quite a range of how things are done. I think things are improving. I think one of the reasons that even though it seems fundamental and obvious that we should have this kind of understanding of the geology and the deposition, is that for people with primarily a geotechnical background, it's not easy to do. It's a new skill set. And I think most of us weren't taught that in school, at least most of us that are a bit older. And it's a challenge. So I think it's working its way into the profession and becoming more recognized as with the importance that it should have.
I know back in my undergraduate days, that one of the required courses we took, and I was glad it was required, was engineering geology. And I think it got drilled into me early on, the importance of that and integrating it with geotechnical engineering, or how integral it is. I wonder these days what your view, Scott, I'll ask you this one, is, with most of our fellow colleagues in geotech have graduate degrees, either the master's or PhD level. And those that you work with or see with interest in numerical modeling are actually doing it. Do they tend to have that background in geology or engineering geology that would be desirable?
You see a wide variety of teaching out there. Some universities emphasize the engineering geology and geomorphology a little bit more than others. So you see a wide variety of students coming out with varying levels of knowledge. I think one of the key elements that any numerical modeler can acquire is the ability to go out on a job site or on a site that's a greenfield site and look around and do a 360-degree view of the site and get an idea of the geomorphology that made the landforms that you're working with and the geology that underlies all of it. I think that that's not taught enough out there, but that's something that was kind of drilled into me while I was kind of coming up in geotechnical engineering, was going out on site and really getting a feel for the landforms so that it would inform your numerical model that you would come at a later time.
Yeah, I think that's something that is exceedingly important. It made me think, when reading your article, it made me think of one time. This was probably about 15 years ago, and a young engineer I was working with, and we had a project with a landslide in both rock and soil, immediately below some major electrical transmission towers. And we were going to work on the analysis, and we had some good engineering geologists involved. And this engineer, I said, we're going to go out to the site and look at it and walk around on the slope and get a feel for it. And he said, oh, no, I don't need to do that. I've got a topo map. The geology's plotted on this topo map. And I said, well, that's all well and good, but we're going to the site. I mean, mainly I wanted to go. One reason I went into geotech is I love being outside, being on job sites or on hillsides. And we went out there and we spent a good deal of time clambering around on the slope and taking notes and taking photographs and so on. And we came back to the office and I said, well, what do you think? Are you glad you went out? And he kind of sheepishly said, yeah, could I go out again tomorrow? There's some other things I'd like to evaluate. And I think I felt really good that that one instance drove home the importance of this thing. And we can't always get out to sites, but how important it is. So moving on, integration of the numerical modeling team, be it one person or more people in a large job. You talk about in your article how it's really important, I think, to really integrate it with the overall project implementation and how important it is right in the planning stage. I imagine, obviously within even proposal preparation, it's optimal to incorporate modeling requirements, and not just the time and effort and cost to implement numerical models, but to get the data that you need. Do you, and either one of you can answer this or both, do you see that integration and coordination routinely, or is it something where it could be done better?
Well, I've seen it kind of both ways. I've seen well-integrated programs where the numerical model comes up at the very beginning, and they're planning on using a numerical model to help understand the overall behavior of the structure. And I've seen it where it's become an afterthought, and they get to the end of a project and they want to add a numerical model tacked on at the end, and they don't have the adequate information that they need for a numerical model. So I've seen both cases in different consultants. So
I'd have to agree with Scott. I'm always happy when a client invites me in early and I can make arguments for related to the site investigation, where things should be done, what tools, and that's not to say that I'm listened to because in every case, because there's budget constraints and other concerns, but I have a chance to make those arguments and at least get some essential items that may have been overlooked. There's a lot of companies approach me after that they have done it. And it seems to be that they may have a routine site investigation approach. They like to do a certain number of CPTs, SPTs, maybe some shear wave velocity tests, and it's just kind of a standard protocol. And in those situations, there's often enough to support an analysis, but there's definitely limitations and qualifications, and that's something that has to come out between me and my client and has to be documented, that there are more uncertainties and unknowns and more things that have to be investigated in the analysis when you have a much less than ideal site investigation.
Yeah, I know I've observed just in, working with modeling efforts, like I mentioned, is when the investigation's not done there, the fallback for a lot of parameters becomes published correlations to this, that, or the other thing. And I've always been, just a little bit uneasy about that. Never, but I guess you try and work with what you have.
One of the difficult.
Oh, go ahead, Mike.
I'm sorry, Jeff. But one of the difficulties with that is when you have to rely too much on published correlations without a lot of perhaps or enough backup to it, is you're dealing with pretty wide uncertainty bands. And a lot of times those aren't directly acknowledged. Either perhaps a parameter is selected that's considered to be conservative, but it may or may not be. And in those situations, you really need to directly investigate for the important parameters what the effect of that unknown range really is.
Yeah. I'm curious, have either of you, you've mentioned times where you were either reviewing or involved in, or being asked to do modeling, and it sounds like the data wasn't there. Have you ever actually said, look, I know you'd like to do a numerical model, but we can't, and here's why?
There have been times. Yeah, there have been times that I've turned down the chance to do a numerical model because of the fact that they just didn't have enough information, and it was being put on as an afterthought.
Yeah, I have as well. Although I'd say that most of the times I've turned down analyses have been just simple business reasons of not having enough time to do a good job and not wanting to promise something that I couldn't deliver. But yeah, there's also cases where the expectations are too high. And in one or two cases where it was pretty clear you didn't need to do an analysis, that wasn't the right approach, at least initially. So there's a wide range of reasons why you may especially an independent consultant may be turning down analysis work.
Yeah. Okay. Well, that's good to hear. I know it's not always easy to say no to it, but, for a variety of reasons.
You know, the consequences of not saying no can be pretty disastrous sometimes.
Yes.
Yeah, definitely. Definitely. I know there's a number of geotechnical engineers that spent too much time with lawyers since when they didn't say no to something, I guess. Moving on, one of the key areas of coverage in your article deals with constitutive models and different types. From one we're all familiar with, more Coulomb, which is used classically in soil mechanics, but the more sophisticated things and classes of models, like for soft soils and so on. And you talked very clearly about the importance of calibrating a model when you apply it, a constitutive model. In your experience, is particularly you, Mike, I guess, because you indicate you do a good deal of peer review. Do numerical models that you see applied, do they usually use the right constitutive model? Or also a kind of a second question, do they sometimes, where it's possible, maybe run more than or evaluate more than one constitutive model?
On the first case, I would say that usually the analyses that I've seen, the constitutive models that are selected are either, very appropriate, very commonly used, or at least they're workable. That you understand, if you have an understanding of the limitations, which impacts your interpretation of the results, they're still usable. But that's not always the case there. I've seen analyses where it was the models that they selected lack the ability to model very key behaviors. And a common thing that I see is trying to use more Coulomb approach, which requires very few parameters, so it's very attractive. But trying to use it in cases where you have a more complex material that maybe is going to generate pore pressures and soften or lose strength. And sometimes there may not be a recognition of that, or there will be an attempt to squeeze the more Coulomb model to crudely model those behaviors. And at that point, I think, there should be some more thought. See if there's a model out there that's well vetted that can handle the type of behaviors that you're trying to model. Other problems that I have seen is, say, with liquefaction, and somebody selects a very appropriate liquefaction model, but may not realize that that model can't do some of the things that it's thinking it's doing, like handling the estimated values of residual strength after liquefaction occurs and after shaking occurs. There might be the assumption it does that, but in fact it doesn't. Or it's not able to handle post-liquefaction settlements, which is a difficult thing right now to do directly in a constitutive model. So that's another problem that I've seen, is just the lack of awareness of what the limitations of some models are. But overall, most of what I have seen is pretty good. As far as using two models, there don't seem to be a lot of situations that really lend themselves to that, either because you can't identify two models that are good fits for your site, or, as more often concern, a factor, there's not enough schedule or budget to really look into things in as much detail as you want, and that may be one of the areas that you can. But there are times when it is done. I know I've seen work by GeoPentech where they looked at several models and evaluated the range, and studies like that are really useful to show the limitations and differences between analyses, especially keeping in mind that your main goal in doing this is not really trying to get the right answer, in terms of deformations or things like that. You're really trying to develop a better understanding of what might happen for your particular site, your particular collection of materials, your prescribed loading. And if you can have two capable constitutive models and use both of them, they're going to have different strengths and weaknesses, and that can help improve your understanding. So it can be a good idea when your site lends itself to it, when your project lends itself to it, and it's probably not considered as often as it should be.
We've had a couple of questions come in the chat. I'm going to ask you these two, and either one of you answer it. Feel free, of course, before we move on to some other aspects. But one of them was, how often do you get additional borings and lab tests after you build your initial model? Or maybe even after you run your initial model and see some outputs? Does that happen very often?
Oh, I've had that happen before, where we've had the opportunity to go out and gather additional information after we ran the initial model and found some behaviors that we wanted to get a better handle on. But it isn't typically the case. Once they've got their site exploration program, a lot of the time they won't go back out and do it again.
Okay.
I agree. I think the one exception perhaps is high hazard structures, high consequence structures. And I've worked on a number of older embankment dams, quite large, storing a lot of water, a lot of consequence if they fail. And in those cases, it's, I wouldn't say common, but to have kind of a phased investigation, even up front, realize that we're probably going to be missing a few things, and we need to plan to go back next year and grab that data. But that's for, as they say, large projects with lots of concern.
Okay. Another question we've had come in on the chat is would you comment on the need for careful definition of numerical modeling outputs and goals between the modeler and the designer who's going to apply the findings of your modeling?
Well, I think it's important that you communicate what your numerical modeling outputs are going to be, and the fact that, like Michael said, it's not necessarily a single number you're coming up with that you're looking for, but insight into the behavior of the model, into the soil, and what possible ranges of soil behavior you could expect. And communicate that to the designer and make sure that they're not focusing on, well, you said my deformation would be a 1/4 inch. And they focus on that one number, and they lose sight of the fact that our numerical analyses, while they can come up with precise numbers, you've got so many uncertainties in your model that you have to be aware of those and let them know that where those factors come in.
I think a common area where that does happen is when the geotechnical analyst is working directly with the structural engineer. And there's often initially a very big difference in expectations for what you can do as a geotechnical engineer. And a common example is you may have a site and there's liquefaction and poor soils and limited treatment, and the structural engineer will come and they say, well, my displacement limits are a 1/2 inch, and I need to, no way can I go beyond that. And the initial response to that is, well, my uncertainty in my answer is going to be way beyond a 1/2 inch. And even before you do the analysis, you come up with an approach that's going to accommodate that uncertainty, and that usually involves some changes on what you're going to do geotechnically in terms of remediation and what you're going to do structurally.
Good. Well, changing directions a little bit to some of the nuts and bolts, the programs that are out there in the commercially available programs, Plaxis and FLAC are, two software packages, modeling software packages that geotechnical engineers commonly select. Scott, could you reflect on what the key differences are between them and maybe particular problems where one is preferred or works better is a word than the other?
Both have their niches that they tend to work better in. I tend to like to use FLAC for models that will experience more deformation, and it can handle large deformations a little bit easier. But FLAC is a finite volume / finite difference method, and it tends to have it's driven more by computational speed of your CPU rather than your memory per se. So it tends to run a little bit slower. Plaxis is finite element, traditional finite element, built for geotech problems. So it can handle deformations, but just not the same way that FLAC can, at least in my experience. But both have their own special problems that they work better for. Mike can probably talk to what FLAC can do probably even better than I can. Now there's even other methods that are coming out, like the material point method, which allows for large runouts and modeling of landslides and things like that, that neither of the programs can handle very well right now.
Yeah. Okay. Didn't think of some of those aspects, the computational speed, since I'm not hands-on, I don't worry quite about that. But anyway,
about
go ahead.
computational speed, what I've noticed is when I started doing these very simple problems took a long time to run in FLAC. You could still make it work, but it took a long time to run. As computers have gotten so much faster, I'm running running problems in less time, but the models that we run now are so much more complex. So it seems to be more important in a way to get the complexity down, to get some of the sophistication in there and the detail than it is to turn out answers really quickly, at least in terms of a FLAC analysis.
We've had another question come in from one of our viewers, sort of associated with this, but this is more related to constitutive models. And the question is, let's say you run two analyses with two different constitutive models. Let's say UBC sand, which you helped produce, Mike, or prepare, and PM4 sand. You'll get two different estimates, not surprisingly. What do you then base your recommendations on?
For me, that question covers a wide range of possibilities. I mean, those two models are different in their formulation. They're fundamentally different. They will likely give you different responses. But depending on what those responses are, both results, may be valid as far as trying to teach you something about the structure that you're looking at. And in many cases, the magnitude of the difference is within the uncertainty range that you're dealing with. So they in some cases, they can be both giving you, valid potential behaviors of the structure, and they're both telling you similar things as terms of trying to make a decision about the appropriateness of the design or the appropriateness of the structure. In other cases, if they are very different, then it comes down to evaluating why they're different and which one do you believe. They're the strengths of one may line up better with the problem that you have, and that's the one you go with, and understand why you are downweighting the other one because of identified limitations for what you're doing.
Sounds like an engineering judgment that we always
Yes.
hear.
Yes.
Critical, obviously, and a key facet of geotechnical engineering. So, well, that question kind of coordinates or transitions into my next question. Is in your article, I was struck by, you made a good point that competent soils, or what we might call well-behaved soils, those that are relatively stiff or strong or not particularly problematic, that when you're working with those materials in a numerical model, the key thing is their initial stiffness and strength, their deformation properties. But not surprisingly, the poorly behaved materials, or potentially poorly behaved ones, looser or softer materials, they're the ones that can be controlling and can lead to damaging behaviors. And you elaborate on some examples like liquefaction and sensitivity, and how those sorts of things complicate modeling efforts. I wonder, what's your opinion about where we stand today in dealing with some of these complicated behaviors? Liquefaction's been touched on already as one, but either one of you want to take a shot at that? Maybe that's a wide open question.
Well, with sensitive soils, especially what I've noticed with like a lot of elastic silts, they're really difficult to model appropriately, but you have to look at what behaviors are you expecting out of your soil. You have to, it goes back to the use of a slide rule. You always had to know the expected order of magnitude of the outcome before you started in on using your slide rule, so that you knew where things were kind of headed. It's the same thing with a lot of these soils. You have to kind of know what kind of behaviors you can expect to get the selection of your numerical model and your constitutive model correct. So it's emphasizing the correct behaviors.
Okay.
Yeah, and I think this is one area where there has been quite a bit of improvement in say the last 20 years, both in terms of the tools available to evaluate many difficult soils, and as well as our understanding of what's important to an analysis. But there's still a long way to go. And a couple of examples I think of is just trying to directly address the aspect or the potential for residual strength of liquefied soils. It's kind of crude the way that we do it right now, and not very fundamental. Another aspect is soils that are going to localize, say, a sensitive clay, or even a clay with moderate sensitivity, and how to handle that in analysis, because it brings up a lot of issues. And I know these are areas that are being looked at into quite a lot at the moment by different researchers, but those are areas that there's a lot of room for improvement in what we're doing, and which is encouraging. It's kind of exciting.
Yeah, I was struck in your article, kind of a key emphasis was related to, variability at a site. Is it a relatively simple subsurface system, or is it complicated, like in a depositional environment associated with a river? That I noted, there's one figure that's included in your article that's an example of how to deal with variable data, and I thought was very illustrative in terms of graphical presentation of that variability. And certainly, you know, there's we can work with probability and other, you know, I guess numerical approaches like you touched about. Do you make use of probabilistic techniques in your work? Or Mike, I guess I'll direct that to you. And if you do, maybe an example of.
Well, the figure you're referring to that was prepared by Ross Boulanger and Dr. Montgomery when he was at UC Davis, and that work has been very useful. And it's one of the more recent of the few attempts that are made to really look at the effect of probability on estimating deformations due to liquefaction. Not so much probability, but variability within the soil. And that type of research provides a lot of good guidance. That technique, though, has not worked its way into practice. I think it's a little bit too cumbersome for what could be done on a routine basis. Even on complex projects, I haven't seen that approach used. But a lot of what we do now is that we look at distributions of the material properties, maybe distributions of penetration resistance, potential distributions in friction angle, and we look at that range. We select representative values, maybe more than one representative value, and so that the values that we're picking are based on distributions of data that we have. But then we go and perform a set of deterministic analyses to try to evaluate the effect of all that variability, which is a useful but still fairly crude way to do it.
Okay. Well, moving back, we've talked a little bit about constitutive models already, but looping back to that, because that was a key item in your article. You talked about, you know, some specific constitutive models and some other classes like for soft soil or seismic loading. An earlier question, you know, we had the mention of two constitutive models related to liquefaction, one of which you helped to produce. I'm curious these days, you know, how is it in terms of selecting constitutive models and what you guys do yourselves, and what you see in your review work of other modeling efforts? Is the selection of constitutive model, is that something that's pretty clear cut in the knowledge base? Like, you know, I've got a site that's soft clay, so I'll use chem clay, or you know, is it still something that's kind of hazy and muddled? Scott, maybe I'll start with you on that one.
Well, it depends on the consultant, really. Sometimes they have a fairly clear-cut choice to make, but it's still kind of a muddled thing, because especially when it comes to liquefaction models, you have a wide variety of them, and as Michael has alluded to, they each have their own benefits and drawbacks, and I don't think they're well enough understood sometimes for consultants to make an appropriate choice as to which is the model they should be looking at for what kind of behavior they're anticipating. So I believe it's still kind of muddled to a certain extent. Some things a little more clear cut than others. For static modeling, the hardening soil model is kind of Plaxis's go-to model for a variety of things. Works quite well for quite a few different types of situations, but it's still kind of a grab bag of which is best for your application.
Okay.
Yeah, it just briefly add on to that. I think it is a lot analysts' preference and experience and comfort. It takes some time to learn a constitutive model, what it does and what it doesn't do, and to understand how well it's been vetted and applied to case histories. That you don't really want to, every time you see a new structure, you don't want to go pick up a whole new set of constitutive models. You kind of start with what you know, and then when they're deficient, then you see if there's something better that you can take the time to learn and appropriately apply.
Yeah, that's something I've seen and heard in over my career. People talking about, particular models that somebody applies. Well, yeah, they developed that and they're familiar with it.
Yeah.
That I think that's just human nature. That when you're familiar with something, there's a certain attraction to applying that. And sometimes probably a little hard to resist when it's not the right thing to do.
That's true.
But very important too.
What's that joke about if you have a hammer, everything starts looking like a nail?
The nail.
Yeah.
Pretty descriptive, I think. And it takes me back to my youth when I loved to hammer nails.
Yes.
I don't know, but anyway, young youth, small child.
Yeah.
Anyway, sticking with constitutive models, you also talk about the importance of calibrating. And obviously, anytime you're applying it, it almost goes without saying, you want to calibrate your numerical model and the parameters you're putting into it, validate those. And you talk about how that can be done by modeling some controlled laboratory tests in some cases. And that seems like, a real good way to go, a controlled condition, reasonably low cost. But do you routinely also see validation, particularly say during construction, early phases of construction, when you're starting to see deformations or movements, that sort of thing, that your model can then predict in a phased approach? Do you do that very much? And we also had a question come in that asks, can you sometimes model a case history from a local area or something? To possibly touch on that, either one of you.
You want to go first, Michael?
It looked like you were going to say something. So.
Oh.
Did you have something you wanted to say?
Oh, no. Go ahead.
Well, I'll play traffic cop here. Mike, why don't you go ahead and say whatever. I'm just picking one random. One of our others.
Right. I think there is, the initial calibration to lab test data, that is really a way to try to make your model site specific. And there are situations where you can help to validate that modeling through what you observe during construction. And I would see deep excavations as one area where you would want to do that. Mining facilities, particularly tailing dams, tailing facilities is another. If you're getting some deformations and you can during construction, and you can compare this construction history with your modeling to see if your modeling has been appropriate or not. A lot of cases don't really lend themselves to that. I do a lot of work on evaluating existing facilities for seismic loads, in which case you don't have those type of measurements, so you can't always do that. I think one aspect, though, and it kind of goes to one point you brought up, is that when you're calibrating the lab test, you're trying to make something site specific. But the other aspect is you also need to validate your modeling approach, that including your numerical solver, how you are building up the model initially, how you're applying the loading. And the best way to do that is through analyzing case histories. And a lot of the good models when they're being developed and shortly thereafter. That tends to be a focus, and that gets into the literature, and an analyst that wasn't involved in the development or in the early use can see that, become comfortable, and know the limits on the approach they should be using. And if you're trying to apply that model in a much different approach, it may not be appropriate until you validated it. So I think that's a separate aspect that it almost comes into selecting constitutive models. You really want to select approaches and models that have been validated in that way.
And a good PhD thesis that kind of goes along with that. Khalid Chowdhury just did his PhD under Ray Seed, and did a comparison of a lot of the liquefaction models, and it gives you a little bit of an idea of what Michael was saying is how they behave for a case history, and how they each tackled that same case history.
Good. You guys did a good job on that one, even though I had, not surprisingly, I expected you would. Well, we're just about out of time, but one last question I have. And we've touched on a lot of the ones that have come in some fashion through the chat, but as we all know, we all have smartphones and laptops and, all kinds of different tools and computational things that we don't even think of as being computational are just part of our daily lives. They're, ubiquitous. And I've noted that, college students and younger high school and even elementary school kids, everybody uses tech tools, as it were, routinely, daily. And certainly, geotechnical engineering is no different as part of engineering. Technical tools are fundamental. So it seems like we probably have now, particularly maybe the younger members of our profession, but those that are entering in the next years too, a huge pool of technical talent who are really comfortable with computing and running some of these numerical models, even eager to do so. But I wonder in your work and in working with staff over, I don't know, the last 15, 20 years or longer, do they really have the bigger picture, or are they, I hate to use the term, but computer jockeys in a way? I mean, do they, they're great at running the programs and putting in data, but do they really understand what's coming out?
Well, I've seen a little bit of both come out of schools. Some people just want to be a computer jockey and want to just input the data and come out with a result, and they may not think about the result as much as they should. I think that has to be fundamental to the education of geotechnical engineers, is that they need to understand where these things come from, their parameters and their uncertainty in the parameters, and understand what the outputs mean in the broader context of your analysis. I think that it's something that's, it may not be learned in school necessarily, but it can be easily taught and mentored in new engineers.
Yeah, I'd second that. I encourage engineering companies, and a lot do this, is that when you have a young person very interested in analyst, is that make sure you develop that engineering experience and judgment. Because if it takes effort, you have to do it deliberately. And if you don't, I think it takes away from the work that you're doing if you don't have that as a part of what you bring into the analysis.
Yeah, I remember many years ago, I had a young engineer. They were actually doing a slope stability analysis, a fairly easy or simple model, as it were, numerical model. But when they came to me with their calculated factors of safety, I asked them how'd they know it was right? And I remember very distinctly getting this answer that started out very confident, but the body language became a little bit sheepish of saying, well, the computer said that. And I was just to make it a short anecdote, as I said, well, I think you need to do a quick hand calculation, even try a chart check from the Navy manual. And sure enough, their answer was correct, but hopefully they learned something from that mentoring some years ago. So, well, we're actually at just a little few minutes over 1 hour past our session. So I want to thank both Mike and Scott for a good lively discussion and tackling some of the questions we came in. We couldn't get to all of them, but I tried to touch on some of the major themes that came in, and remind everybody, and I'll turn it over to Brad, but you can look at this on YouTube very soon. So thank you to both of you. Brad?
Thank you.
Thanks, Jeff, and thanks, Michael and Scott. This was a really good discussion. Thanks, everybody out in the world, for submitting your questions. What a great discussion we had today. My reminder to you is to click that little subscribe button that you see below the video box, and then click get notifications, and you will get all the wonderful content that we have on the GI YouTube channel. Thanks again to our sponsor, Aero Aggregates. Again, you can find out more about them at aeroaggregates.com. I will make one pitch today for our 25th anniversary Student Participation Fund campaign. Past President Ed Kavazanjian donated $125,000 to the GI as a matching gift at the beginning of this fiscal year, and we're hoping to match it so we can get Ed's full gift. Go to the Geo-Institute website at geoinstitute.org, and you can find out all about the different giving levels we have and how we can take full advantage of Ed's matching gift. We have these handsome 25th anniversary GI pins. That's what you get for a $25 contribution. $250 gets you a pin and a nice Nike Dry Fit GI shirt. So you're going to want to take advantage of that. If you enjoyed GeoStrata Extra, and I hope you did, we do this every 2 months. So look for the next episode in late March. We'll pick an article from the March-April issue, and it will be as fantastic as the one we did today. And finally, our next live stream will be in approximately a month from today, and it will be part of our diversity and inclusion series. So look out for that as well. And again, thanks, guys, for doing this today. What a fantastic discussion. And hope we see everybody soon. Thanks for tuning in.